This tank was certified as safe. The numbers said so. The man who signed off moved on. It held 2.3 million gallons of molasses, 15,000 tons, in the middle of a city. On January 15th, 1919, it failed. The wave was 25 feet high, 35 miles an hour, through a neighborhood full of people. 21 people killed, 150 injured, and the tank had been warning them for months. The question isn't just why it failed, it's what they believed, and why that belief made complete sense in 1915. That belief was built step by step from the moment this tank was commissioned. We're going to reconstruct it, because when you understand what they thought they knew, the failure hits completely differently. The tank was commissioned in 1915 by United States Industrial Alcohol, USIA, who needed to store the raw material for their industrial alcohol operation. The man they put in charge of building it was their treasurer, Arthur Gell, an accountant. No engineering qualifications, no licensed structural engineer was hired. Gell reviewed the drawings himself, approved the design, and authorized the build. The blueprints looked like engineering, dimensions specified, plate thickness calculated against exactly one load, the weight of the molasses pressing outward on the walls. That formula is real. Pressure equals density times gravity times height of liquid. It is correct for a liquid that never changes temperature. The temperature variable is simply not there. They put this tank here because the rail connection made sense. The neighborhood didn't factor into the engineering calculation. It would factor into the death toll. They ran one test, filled it partway with water. The seams held, everyone signed off. Each rivet hole punched through the plate was considered a standard feature. The stress around it was assumed to flow smoothly past the cutout. It didn't, but this would only be visible to the investigation, not the design team. The weld design looked solid. Every number cleared the bar. On paper, this was a competent piece of engineering. Within weeks of service, the tank started leaking. Slow seepage from the weld lines, enough to stain the street. Children came to lick the walls. USIA's official response? The leaks were normal settling. The tank was fine. No structural engineer was consulted. The paint budget was approved. At the metal level, invisible to anyone on the outside, each rivet hole was doing something the design hadn't accounted for. At the edge of the circular cutout, stress concentrated sharply, and that concentration had begun to open a crack. Every fill, every emptying, every pressure cycle flexed the metal fractionally. Each flex extended the crack a little further. The tank was counting cycles. Arthur Gell's response to the leak reports: paint the tank brown so the stains wouldn't show. And here is the assumption that everything rested on: temperature. The engineers never calculated what heat would do to the pressure inside that tank. It wasn't in the design, it wasn't in the standard, it simply wasn't in anyone's mind. On January 13th, a tanker arrived from Puerto Rico. Its hold carried fresh molasses, warm from Caribbean fermentation, pumped directly into a tank that had been sitting in Boston winter for days. A 40-degree differential between the incoming liquid and the surrounding steel. Nobody ran the number because nobody had written that number into the design process. The tank was full. Warm molasses sat inside cold steel, slowly transferring its heat. The pressure was building, and nobody knew to measure it. January 15th, 1919, a Wednesday. The temperature had climbed above freezing for the first time in days. The pressure inside the tank was at its highest point since the tank was built. On paper that morning, the tank was fine. Every engineer who had touched the project would have agreed. The numbers said so. When you heat a liquid, it expands. Every degree pushes the molecules further apart. The same mass of molasses occupies more space, but the tank walls are rigid, so the pressure on every weld goes up instead. Cold molasses is dense. The outward force on the walls is the one the engineers calculated. Warm molasses expands. Same mass, more volume, rigid walls. The pressure increase isn't dramatic. It's 12 to 15% above the static load. That's enough. The combined pressure, weight plus thermal expansion pushed past the design load. Not catastrophically, not all at once, just past it. At each rivet hole, the actual stress was triple what the design had assumed. The cutout edge wasn't a smooth pathway, it was a stress trap. By January 14th, the cracks at the rivet holes were deep. The warm Caribbean delivery had added pressure, and the crack tips had advanced. At the weld toe, the sharp edge where the weld bead meets the plate, stress doesn't distribute evenly. It concentrates. The geometry forces it. This isn't a defect, it's physics. At that stress concentration, a crack had already started, probably months earlier during one of the fill events Arthur Gell had painted over. The crack is there, growing slowly, invisibly. Each fill cycle, each temperature differential, each delivery of warm molasses from the south pushes it a fraction further. The January 13th delivery of warm molasses adds a thermal pressure spike. The crack advances. January 14th, the warm molasses has been in the tank for 24 hours, still transferring heat to the steel, still raising pressure. The residual intact metal at the crack tip is now thin. It is carrying stress it was never designed to carry alone. January 15th, 12:25 p.m. The temperature is above freezing. The warm molasses has been in the tank for 48 hours. The crack reached through. The weld gave way. The pressure behind the first fracture created a stress wave that ran around the circumference. Seam after seam gave way in rapid sequence. The whole structure came apart in under 3 seconds. 2.3 million gallons of molasses hit Commercial Street at 35 miles an hour. The wave was thick, not like water, like something with mass and intent. It carried steel panels the size of rooms. It knocked buildings off their foundations. The elevated railway, steel columns and concrete footings, was knocked partially off its foundation. If the wave could do that, it could do anything in its path. Rescue took hours. The molasses was cooling, thickening, setting around the victims. Horses were trapped and had to be shot where they stood. The metallurgical analysis confirmed it. The crack had been there a long time. The warm Puerto Rican molasses had added just enough pressure to push it through. The leaks weren't settling. They were evidence. The lawsuit was unlike anything American engineering had seen. A judge appointed a special auditor to examine every engineering decision, every calculation, every signature on the project. It took 6 years, more than 3,000 pages of testimony. The first major structural failure lawsuit in United States history to examine the engineering process itself, not just the accident. The auditor's findings? No licensed structural engineer had been involved in the design. No thermal analysis had ever been performed. The test had used water at half capacity and had never been repeated at service conditions. They tested for the wrong thing. The test passed because it didn't represent reality, and nobody went back to check whether it did. The metallurgical report found cracking at dozens of rivet sites across the failed panel. This wasn't sudden failure. The tank had been degrading for years. The leaks were the external sign of internal damage nobody was trained to read. The engineering response was permanent. The sharp corner at the weld toe, where every crack in this disaster originated, was eliminated by specification. A radiused fillet replaced it, smoothing the stress path through the joint. And thermal expansion became a required term in the pressure calculation. The assumption that temperature didn't matter was removed from the standard. The equation was completed. Every large storage tank built in the United States today, at a chemical plant, a brewery, a fuel terminal, carries a weld geometry specification and a thermal load calculation that did not exist in 1915. They exist because of Commercial Street. The disaster also changed something larger. Massachusetts moved to require that structural drawings be signed off by a licensed professional engineer, a qualification that barely existed as a legal category before this disaster. the PE stamp, the engineer's signature that appears on every structural drawing in the United States today. That requirement was shaped in part by what happened on a Boston street in January 1919. The mental model from this disaster fits in one sentence. The tank was sized for cold molasses. No one calculated what warm, expanding liquid would add to the pressure. The engineers called the leaks normal. The physics called them a countdown. The tank was never rebuilt. The site was turned over to the city. What remained was not the structure, but a harder, more honest calculation that had to account for what the liquid actually experienced. Every assumption that wasn't written into the standard in 1915 is written in now. The gap between the blueprint and reality is smaller because Boston made it smaller at a cost that should never have been necessary.